This lesson's focus is to generate new Taylor series representations based off prior Taylor series representations we've already learned. For instance, we're going to create the Maclaurin series of f of x equals sine of 2x. Now remember, a Maclaurin series is a Taylor series whose center is 0. And we could go through the whole process of doing a Taylor series, or in this case a Maclaurin series, by generating nth order derivatives and generate those values of terms. So as you can see, I've quickly done the work where I've gone from f of x all the way up to the fifth derivative. I've plugged in the center equals 0, again, Maclaurin series. I found the different coefficient numerators, 0, 2, 0, negative 8, 0, 32. Took all those, divided by their denominators n factorial respectively, 0 factorial, 1 factorial, and so on. Multiply that coefficient by x minus 0 raised to the 0, x minus 0 raised to the first, which is just x raised to the nth power. I could do all that and come up with my final answer. Or I could just take what I already know about sine of x. I could use its Maclaurin representation, its summation, negative 1 raised to the n, times x raised to the 2n plus 1, all over the quantity 2n plus 1 factorial as n goes from 0 to infinity. I could rewrite that as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And in some respects, I could do a u substitution. I could say my u is like 2x. And so instead of saying sine of x, I could say sine of u, put a u here, put u here, and just replace that now with 2x, which is much easier in red as you can see in the PowerPoint. I just put 2x here, 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 here. And if I do that, I can come up with 2x minus 8x cubed over 3 factorial. Well, there's the 2x, and there's the negative 8 over 3 factorial x cubed, which is that piece, and I do get my 32 over 5 factorial x to the 5th. It seemed to go a lot faster. And then I could even clean it up and say, hey, my sine of 2x is equal to 2x minus 4 thirds x to the 3rd plus 4 fifteenths x to the 5th minus 8 over 315 x to the 7th, and so on. Just remember one more small detail. If your Maclaurin series for sine of x converges for all reals, your interval of convergence then will be all reals for sine of 2x. For our final example, let's find the Maclaurin series of f of x equals x cubed times e to the 4x. We will need our Maclaurin series representation of e to the x. That's the summation of x to the n over n factorial as n goes from 0 to infinity. If you wish to expand the series out, it would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. And like the last example, we will do some substitution. We will replace x with 4x. So now our summation is going to be of the quantity 4x, where the quantity is raised to the nth power all over n factorial. And all our terms where we used to have x are now going to be replaced with 4x. So if we had an x and was squared, the quantity 4x will now be squared, and the 4x quantity will now be cubed, and so on. But we're not quite done because we're looking for x cubed being multiplied. So how about we just simply multiply everything by x cubed, which means we can multiply x cubed to our summation. We can multiply x cubed to every one of those terms in our expanded series. And with some algebraic tweaks, knowing our exponent rules, knowing that x to the n times x cubed is the same as x to the n plus 3, by distributing x cubed over each of the terms, we can come up with our brand new Maclaurin series representation. We can come up with an expanded series that simplifies as x cubed plus 4x to the 4th plus 8x to the 5th, and so on. We even could go on and say that we know our interval of convergence, because since the Maclaurin series e to the x converge for all reals, so will x cubed times e to the 4x also converge for all reals. What we're saying is this. There are multiple ways of generating new Taylor series representations, or simply power series representations. We've learned to substitute. We've done it with x being replaced with 2x, and we've replaced it with 4x. Just now, we multiplied by x cubed, so you can multiply. What's stopping you from dividing? We've already shown in prior lessons that power series can be differentiated and integrated. That's how we came up with tangent inverse and ln of 1 plus x. So we have all these different ways that we can generate these new representations. And that's the end of the lesson.